Hello, everybody. My name is Chana Samanathan, and I'm a specialist solutions architect focusing on IoT and robotics at Amazon Web Services. Welcome to the session on scaling for complexity, architecting for performant embedded devices at the edge. I'm really happy to be here with all of you. So these next few slides highlight the type of questions we get from our customers and which we try to help them solve. As you know, embedded devices with multi-sensor data sources are proliferating at an accelerating rate. Devices must be manufactured, designed, installed, connected, and controlled through 7 distinct logical layers to securely connect and interact with complementary cloud-based and edge-based components to deliver business value. These Internet of Things applications must gather, process, analyze, and act on data gathered by these connected devices themselves. And it is these types of questions which we get from our customers asking for various things about IoT. Therefore, we work back from these questions to see how we can best help our customers, and I'm here to share some of those methods with you today. In the paper that was submitted to the Embedded World Congress, you will discover how to make informed trade-offs with the end-to-end architecture challenges based on your business and performance needs. We will discuss today some of the best practices and relations between the design and manufacture, the edge, provisioning, communication, the ingestion, the analytics, and application layers, and how a properly designed edge architecture allows for complex scaling scenarios. And it is this scaling of complexity which we believe is the key when building for various performant IoT applications. Consider in 2025, as many as 152,200 IoT devices will be connecting to the internet every single minute. The number of cellular IoT connections is expected to reach 3.5 billion in 2023. AI, machine learning, and real-time data processes delivered by IoT solutions are driving cellular IoT devices boom. Smart factories in North America are expected to be worth more than 500 billion this year. The manufacturing process is being revolutionized with connected devices driving substantial productivity increases. Businesses could spend up to $15 trillion in IoT by 2025. Businesses are well aware that IoT devices potential to add value to their businesses and are investing heavily in the technology. So, with this acceleration of growth, it becomes even more important that IoT devices must be designed, manufactured, installed, connected, and controlled through the following 7 layers to securely connect and interact with complementary cloud and edge based components to deliver business value. These layers are very similar to the Open Systems Interconnection model, the OSI from a networking model. The OSI model is a conceptual model that describes the universal standard of communication functions of telecommunication system or computing systems without any regard to the system's underlying technology or internal specifications or any kind of protocol suites themselves. This layered approach for protocols can be applied to the IoT architecture stack as well, where each layer can be modified as needed to achieve a specific level of service to the layer below it. Therefore, the objective is the interoperability of all the diverse communication systems containing standard communication protocols through the encapsulation and de-encapsulation of the data itself for all network communications. So each intermediate layer serves as a class of service and functionality to the layer above it and is served by the layer below it. So the splitting of the different abstraction layers is what we believe drives the business value through for IoT. After all, no customer ever approaches a vendor and asks to buy IoT, nor would an IoT provider just sell IoT itself. At AWS, we support our customers' business needs by asking them a very fundamental question. If you knew the state of everything and could reason on top of that data, what business problems would you solve? Our mission is to make sure that you can know the state of everything, all of your devices, and that you can reason on top of that data so that you can truly solve the business problems themselves. Therefore, if there were an IoT OSI model, it may look something like the following, where we group the layers into larger constructs from the top down. You have business value, big data, cloud, and finally the fog. So you can group these the top two layers into a business value, the next one into a big data, the next one into a network layer into the cloud, and finally the bottom two as the fog, not cloud and not the edge, but somewhere in between there. We would have people and processes and the applications that they use to derive the business values in one group, and this group would consist of layer 6, where customer applications would need to be created for presenting specific thing data. It would also include layer 7, where the decisions for the business would be made based on the thing and applications and data itself. Next would be the data ingestion and the analytics, which is traditionally referred to as big data. This would consist of layer 4, which is responsible for the ingestion of the thing data and harvesting specific trends. These trends are further evaluated at layer 5, which is responsible for various types of reporting, mining, extraction, and even running machine learning models against the stored data. Below that, the construct is the general infrastructure of the business, also known as layer 3. For simplicity, we consider that to be the cloud. That cloud infrastructure can be in the form of a public cloud, a private cloud, a hybrid, or even a managed cloud. It can even be in the form of on-premise infrastructure. Lastly, we have the edge construct, the edge consisting of the connectivity and the edge computing at layer 2, and the actual things at layer 1, which includes various devices, sensors, controllers, etc. Together, these four constructs help to balance a well-architected framework for IoT implementations. The framework consists of operational excellence, security, reliability, performance efficiency, and cost optimization pillars. Now, the AWS Well-Architected Framework helps you understand the pros and cons of the decisions that you make when building systems on AWS. Using this framework allows you to learn architectural best practices for designing and operating reliable, secure, efficient, and cost-effective systems in the cloud. The framework provides a way for you to consistently measure your architectures against best practices and identify areas for improvement. We believe that having a well-architected system greatly increases the likelihood of business success. So, in the context of IoT, we focus on how to design, deploy, and architect your IoT workloads in the AWS cloud. When architecting technology solutions, you must make informed trade offs between these pillars based upon your specific business requirements. So now as I go through the next 7 layers here, please keep in mind that I'm purposefully keeping out any information which is in the academic paper so as to keep any AWS services and mechanisms on how to implement these layers and best practices out of this presentation. Please refer to the paper for more details. Thank you. So first of all, the design and manufacturing layer. The design and manufacturing layer consists of product conceptualization, business and technical requirements, gathering, prototyping, module layouts and design, and finally the component sourcing and manufacturing the devices themselves. Decisions are made in each phase impacts the next logical layer of the IoT workload described below. For example, some IoT device creators prefer to have a common firmware image burned and tested by the contract manufacturer themselves. This decision will partly determine what steps are required during the provisioning layer. So you may go a step further and use a unique certificate and a private key for each device during the manufacturing. This decision will impact the communications layer since the type of credential can impact the subsequent selection of the network protocols. If the credential never expires, it can simplify the communications and provisioning layers at the possible expense of increased data loss or any kind of risk due to the compromise of the issuing certificate authority itself. Next, we have the edge layer. So the edge layer of your IoT workload consists of the physical hardware of your devices, the embedded operating system that manages the processes on your device, and the device firmware, which is the software and the instructions that are programmed into your IoT devices themselves. The edge is responsible for sensing and acting on other peripheral devices. The common use cases are reading sensors connected to an edge device or changing the state of a peripheral based on a user action, such as turning on a light when a motion is activated and such. Next, we have the provisioning layer. So the provisioning layer of your IoT workload consists of the public key infrastructure, the PKI, used to create unique device identities and the application workflow that provides configuration data to the device itself. When you provision IoT devices, you must install a unique cryptographic credential onto them. By using X509 certificates, you can implement a provisioning layer that securely creates a trusted identity for your device that can be used to authenticate and authorize against your communication layer. So the X509 certificates are issued by a trusted entity called a certificate authority or CA, while X509 certificates do not consume resource on the constrained devices due to memory and processing requirements. They are an ideal identity mechanism due to their operational scalability and widespread support by standard networking protocols. Next is the communication layer. The communication layer handles the connectivity, message routing, and remote devices, and routing between devices and the cloud itself. The communication lets you establish how IoT messages are sent and received by the devices, and how devices represent and store their physical state in the cloud itself. You should have some type of publish subscribe broker to help you build IoT applications by providing a managed message broker that supports the use of the MQTT protocol to publish and subscribe to IoT messages between the devices. Next is the ingestion layer. A key business driver for IoT is the ability to aggregate all the disparate data streams created by your devices and transmit the data to your IoT application in a secure and reliable manner. The ingestion layer plays a key role in collecting device data while decoupling the flow of the data with the communication between the devices itself. Next is the analytics layer. One of the benefits of implementing IoT solutions is the ability to gain a deep insights about the data and what's happening in the local or edge environment. A primary way of realizing contextual insights is by implementing solutions that can process and perform analytics upon that IoT data. You might have storage services. So IoT workloads are often designed to generate large quantities of data where we have to ensure that this discrete data is transmitted, processed, and consumed securely while still being stored durably. Next, you might have analytics and machine learning services there also. So after your data reaches a central storage location, you can begin to unlock the full value of that IoT data by implementing analytics and machine learning on the device behavior and the data itself. With analytics and machine learning, IoT systems can implement proactive strategies like predictive maintenance or anomaly detection to improve the efficiencies of the system. Next, we have the application layer. So the application layer for AWS IoT provides several ways to ease the way the cloud native applications consume data generated by IoT devices. These connected capabilities include features from serverless computing, relational databases to create materialized views of your IoT data, and management applications to operate, inspect, secure, and manage your IoT operations directly. The management applications have the purpose of management to create scalable ways to operate those devices once they're deployed in the field. Common operational tasks such as inspecting the connectivity state of the device, ensuring device credentials are configured correctly, and querying devices based on their current state must be in place before you launch so that your system has the ability and the required visibility to troubleshoot any kind of application that can come up. Next, we have the application layer. So the AWS IoT provides several ways to ease the way cloud native applications consume data generated by IoT devices. These connected capabilities include features from serverless computing, relational databases to create materialized views of your IoT data, and management applications to operate, inspect, secure, and manage your IoT operations. You have management applications that is used to create scalable ways to operate your devices once they're deployed in the field. Common operational tasks such as inspecting and connectivity state of a device is important because you have to ensure that the device credentials are configured correctly, and querying the devices based on their current state has to be in place before any kind of launch so that your system has the required visibility to troubleshoot the applications themselves. Then in addition to that, you have the user applications. So the user applications are going to be managed applications and other and internal and external systems that need different segments of your IoT data for building different applications. To support end consumer views, business operational dashboards, and the other net new applications you plan to build over time are going to need other technologies that can receive the required information from your connectivity and some kind of ingestion layer to format them and to be used by these other systems. Then you have database services. So the database services can consist of NoSQL or SQL. So while a data lake can function as a landing zone for all this unformatted IoT generated data, to support all the formatted views on top of your IoT data, you need to have some way to complement your data lake with structured and semi-structured data sources. So for these purposes, you should leverage both NoSQL and SQL databases. These type of databases enable you to create different views of your IoT data for specific and distinct end users of the applications. Then you have the compute services. So frequently IoT workloads require application code to be executed when the data is generated, ingested, or consumed or realized. So regardless of when your compute code needs to be executed, serverless compute is a highly cost-effective choice. Serverless compute can be leveraged from the edge to the core and from the core to the applications and analytics. In conclusion, the AWS Well-Architected Framework provides architectural best practices across the pillars for designing and operating reliable, secure, efficient, and cost-effective systems in the cloud for IoT applications. The framework provides a set of questions that you can use to review an existing or proposed IoT architecture, and also a set of AWS best practices for each of those pillars. Using the framework in your architecture helps you to produce performant, stable, and efficient systems ready for scaling, which allows you to focus on your functional requirements and your applications directly. And finally, as we say at AWS, build on. Thank you. If you have any questions, please reach out to me directly at my email or connect with me on LinkedIn. Thank you.